Morning, my name is Gopal. Morning, good afternoon, good evening. My name is Gopal Nagendra, calling from Bangalore, India. So today we are going to be talking about complex and dynamic composite data recovery. So we'll briefly go through the introduction, the benefits, input-output requirements if there are any, test cases that we have put in the TPL library, which can be used as template to get familiar with the capability, and tips for optimum usage. So the main thrust of this project is that if we go to this last bullet here, we have had lamina or ply output available for statics and normal modes for a long time. So now we have extended this capability so that for dynamic solution sequences, that is for frequency response direct and modal, transient response direct and modal, and for random analysis, we will have a ply or lamina output. So the same idea has been carried forward from the static analysis in NASRAN to enable ply or lamina output in the dynamic solution sequences. So this is primarily a post-processing or a data recovery operation. So we go through the entire finite element operation. Once you have obtained the displacements, then we obtain the strains for the laminate. Then the same principles of classical lamination theory apply, and then from strains we get the stresses, etc. So similar to statics, the element types which are supported for composites are quad 4, triad 3, quad 8, triad 6, quad R, and triad R. The response types for composites, again, ply stresses and strains, failure indices, and strength ratios. Property types are PComp and PComp-G. PComp-G, as many of you may be aware, allows us to specify the global ply IDs. GPR sort, which is also supported for statics, allows you to sort the output by global ply IDs. So on the PComp-G, you can, for example, specify your global ply ID, and GPR sort in the case control then allows you to sort your output by global ply IDs. In the statics context, sort 1 is important, but once we move into dynamics, we need to be able to support both sort 1 and sort 2. So both sort 1 and sort 2 are supported, and the way you request sort 1 and sort 2 is in the standard manner in case control, where, for example, stress within bracket sort 1 or within bracket sort 2 will trigger one or the other. Sort 1, basically you sort your output according to, let's say, for example, frequency response. You'll have the outermost loop as frequency followed by element ID followed by ply ID. For sort 2, it will be element ID followed by ply ID followed by your frequency or time step. And again, you can request either real imaginary or magnitude phase output by specifying either IMAG or phase in your case control. Benefits. This is going to benefit all users of composites who are interested in getting lamina or ply level output, particularly aerospace users who we know use composites quite heavily. And especially for large problems, if you go to the big guys like the Boeings or the Lockheeds, they have extremely large problems with many thousands of elements and thousands of time steps, and maybe hundreds or even thousands of plies per element. So the thrust of this project has been to make the processing as efficient as possible, because for very large problems, you would like to have the output in a reasonable manner. And to the best of our knowledge, the dynamics composites may not be available with our competitors. I don't know. Yesterday, Ted Wortham mentioned that maybe some of these have. So maybe the field personnel will be the best people to know whether some of these other softwares, they support the dynamic composite capability. So the reason why we would like to have ply level responses obviously is because it is more accurate and a realistic representation of the stress state rather than the equivalent homogeneous stress values. Failure normally occurs at the ply level, and each ply can have a different orientation and a different set of material properties. So obviously the designer would be more interested in getting the ply level responses rather than a kind of an average homogeneous value for the stresses. Input and output, they follow the same pattern as for statics. So those of you who have used the static composite capability, there is no new input to invoke the dynamic composite capability. The presence of the PComp or the PComp G triggers dynamic output at ply level. So the same kind of ideas that you need to have stresses and forces in your case control for getting your failure indices, etc. Similarly, output, there is nothing specific required. You don't need any parameter or anything. The output is also similar in flavor to that for statics, except that now we have also a ply level output for forcing frequency or time step. So if you have a standard, let's say, frequency response analysis, what used to happen before this capability was introduced was that you would get forcing frequency and then the stresses or strains for all the elements. So then now you also have forcing frequency, then for each element, for each ply, you will get the stresses or the responses. The param no-comps -1 output stresses for the equivalent homogeneous shell. So if you don't want it on a ply-by-ply basis, then this will give you a kind of a smeared value for the responses. We have put in a bunch of test cases in the TPL library. There are about 12 or 13 of them. And they are in a folder called PCompDyn. So I would encourage those of you who want to get more familiar with the capability to look at each of these test cases. They are very simple test cases, and the basic idea here is to outline or to make the user familiar with the different solution sequences, element types, the sort 1, sort 2, GPR sort, and how to get the laminar stresses, strains, strength ratios, etc. GUI support is limited. We have OP2 support for transient responses. We are working on XDB support and frequency responses for both OP2 and XDB for the future. So as I mentioned, the main thrust for this has been that for very large problems, you are introducing another level, that is the plies. So that if you have a dynamic situation, say for frequency response or transient response, if you have, say, 100,000 elements and you have got, say, 1,000 time steps, and if in addition you are, let's say, introducing 100 to 500 plies per element, then obviously, performance and efficiency considerations become very important. So here we are offering some tips, as to how to control those. So for small problems or medium problems, obviously, performance issues are not that important an issue. So for large models with many composite elements time steps, we may we may notice an increase in the I/O times and CPU times. GPR sorts it in the global ply order, so unless it is required for very large problems, be careful because it may involve expensive multiple key sorts, so it may increase the CPU time. So one way to reduce the output is, let's say, in most of the situations, if there are, say, 100 plies per element, you may be interested only in the extreme plies at the top and the bottom. So if that is the case, then you can put S out is equal to no on your PComp card so that you get output only for the extreme plies, and this is a way to reduce the voluminous amount of output you may get and also to reduce the CPU time and maybe the I/O times. Between sort 1 and sort 2, CPU-wise, sort 1 is the preferred option for dynamic composites. This goes against the, the traditional dynamic analysis where most of the time sort 2 is used. This is again because of the, 3 levels that are involved here. So sort 1 1 may be the preferred option. So anyway, you need to look at the problem that you are trying to solve and make your own judgment. This is just to point out that you need to look at sort 1 a little bit more carefully in the dynamic composites context. If you're using GPR sort, again for large problems, these are all for large problems, it may be more efficient to use sort 1. Thank you, that's all I have.